minus y sub I bar. I can't write that in there, you guys. I'm integrating respect to x. I guess I better change that. I think another name for the y sub I is, well, what's this curve going to look like? So you're saying y is equal to square root of x. Then I think another name for y sub I is the square root of x sub I, just square root of x, minus the y value down below, but the y value down below is going to be y sub I bar. But what's the equation of this curve if y is going to be isolating that equation? Yeah, I heard that. It's going to be negative root x. And so I'm subtracting off a negative root x. And I'm basically integrating 2 times root x with respect to x. My bounds of integration are going to be one x value extreme to another one. Do you guys agree? And I think in this example, I'm going to get an answer, which is nothing more than, whoops, not an interval, which is nothing more than 2 times. Let's anti-differentiate x to 1 half. I'll got the exponent by 1, x with 3 halves. Divide by the new exponent of 3 halves, which is multiplied by its reciprocal, which is 2/3. And the value from here to here. But that's just going to give me a 4/3 times 4 times the square root of 4, which in the end turns out to be 32/3. That's the area bounded by those regions. But now that I still got 5 minutes left, that was so much fun. Let's do it completely over again. This time. I'll use my green pen. What would happen if I looked at these horizontal rectangles instead? And look at these 2 points. How about x sub I comma y sub I and my x sub I bar comma y sub I bar? For me to set up an integral, because it's a horizontal bar, then I think this vertical width is going to be an infinitesimally small width, which I might refer to as delta y, because it's changing the y direction. But when I take the limit of a ring on sum, that'll become a dy in the integrand's position. So I think the area is going to be represented by looking at some stuff, and I'm integrating respect to y. I just think when it comes to the horizontal length of that rectangle, it's going to be the large x value, which is x sub I, minus the small one. Now, no matter where I'm on this line, what's the value for x sub I?
4.
It's always going to be 4. What about a value for the x sub I bar, but give it to me in terms of y? It's going to be y squared. My bounds of integration, I forgot you guys, are from 0 to 4. What do you know? Huh? A new flag to which I pledge my allegiance. Since I'm integrating respect to y, I think I need to find the y chorus of these points of intersection. Piece of cake. If x is 4 right here at that corner point, plug in 4 in for x, isn't y going to be 2? So, yes or no? Am I integrating from negative 2 to positive 2? Yes, I am. I'm too tired. I don't want to do it. Because there's so much symmetry, can I just cut it in half and double the result?
Yep.
But that means in actually anti-differentiating this beast, that gives me 2 times a 4y minus 1/3 y cubed as y ranges from 0 to 2. But now evaluating, that gives me 2 times an 8 minus an 8/3. But that's just simply a 16/3 times, I don't know, is that 3 minus 1? But that gives me 16/3 times 2, which is 32/3. Oh, thank goodness, it's the same number. My point is, sometimes it might be more advantageous to integrate respect to variable y. Just draw your triangles or rectangles appropriately.
How would you phrase the question for us to know which way you want us to do it?
I think with this question, the perfect instruction would be compute the area and leave it up to you. I promise you, in the very near future, particularly when we jump into higher dimensional space, I'm talking about tomorrow, you're going to really want to do it one way as opposed to the other. In a test situation, I'll leave it to you to decide. I'll make sure life is miserable in one direction to force you to play chess and look ahead and determine which technique would be more appropriate.
You're probably very good at chess.
You will be after next week. You guys, any questions about what I just said? Gosh, I feel like I just bored you to death today. I'm so sorry. maybe more exciting tomorrow because we're jumping higher-dimensional space.
Get some cool stuff tomorrow.
Everything's fun high dimension.
Next 3 chapters are awesome.
What's that?
I said the next 3 chapters are awesome.
Oh, they're all awesome. Yeah. Right. Oh, homework.
Yeah.
Oh, goodness. Shoot, I yet again don't have any.
Eva?
No, I got it. I remember it. And you guys, I don't know if I said this, but I really will try every day to bring my book in case you don't yours, because
Exabyte,
are we only in section 6.2?
Yep.
yeah, Lexabyte. On the other side, exabyte.
You guys, for the rest of this chapter, integration is an absolute piece of cake. I'm not extending your notions of integration. I'm just looking at particular applications to value integrals, nothing more. So don't think of the remainder of chapter 6 as being very heavy at all. It's just playing a game with goofy little pictures. We just need to be careful how we're drawing the pictures. So section 6.2. I want you to take a peek at the following.